Hi, everybody. We are back to continue our discussion of interval estimation, and the focus of this particular module is to really look at how to think about reverse engineering the sample size in order to support an acceptable level of margin of error. And to kind of motivate this topic, we're going to go ahead and look back at an example we saw in an earlier segment where we were dealing with an automaker that was trying to comply with an EPA mile per gallon regulation. And in this example, the automaker had used a sample size of 40 to construct a 95% interval for the population mean mileage for these mid-size car models. And the size of that sample in that example, I'm going to kind of show you where we got that from. So what we're going to do now is we're going to back up for a minute, and we're going to make the assumption here that before our automaker decided to use this mileage, this sample size of 40, that they started prior, and before selecting 40 cars, it randomly selected only 5 vehicles. Okay, so very, very small sample. You notice we're under that 30 threshold. And if we're only selecting 5 vehicles here, okay, then there's going to be implications for the margin of error when we construct a confidence interval. Okay, now our goal is to still do the same thing. We want to go ahead and we want to determine a 95% confidence interval for the true mean for these mid-size cars to see whether or not the manufacturer would qualify for this tax credit. And again, in this situation, with only these 5 mileages here, we're given a sample mean of 31.3 miles per gallon. There's a sample standard deviation of 0.68. Notice that is S, that is not the population standard deviation. So we're back in this situation where we're going to be able to use the T distribution this time. In the previous example, when we had first looked at this case study, we had only applied the normal distribution using our Z table. So the first thing we're going to do here is we're going to construct a confidence interval at the 95% level for the data that we've extracted here using the sample size of n equals 5. And that is the first thing we're going to do. So again, here's what we know. Okay, and in order to construct that confidence interval, again, we're going to have to figure out our t-value thresholds for both the min and max of that confidence interval by figuring out how many standard errors away from the mean define the 95% confidence range. And to do that, we need to know our degrees of freedom. In the case of a sample size of 5, our degrees of freedom is, again, n-1, will be 4 degrees of freedom here. And now we can go to our t-table, and we can look down the 95% confidence interval column. We can look for the 4th row, or row number 4, corresponding to 4 degrees of freedom. So take a moment. You can pause the video now if you'd like to do that. And what you should find is that the t-value that corresponds to 4 degrees of freedom and a 95% confidence interval is 2.776. Okay, now we are in a good spot to go ahead and plug and chug, given that we don't have enough observations to exploit the central limit theorem, and we did not know the population standard deviation. We've estimated it here. So we're going to go ahead, plug our values into our margin of error formula. We're going to plug x bar in for x bar here. And we can go ahead and see that the margin of error for this confidence interval is about 0.84 on either side, 0.844 exactly here. So if we take 31.3, we add and subtract that margin of error. This gives us a confidence interval that ranges from 30.456 to 32.144. Now, if you remember back to the original example, the threshold that the automaker needed to meet was 31 miles per gallon. Now, the problem they face here is the bottom of their confidence interval violates that lower limit. Okay, the sample mean might be above it, right? The sample mean, 31.3, is above it, but we saw before that could really just be a function of the sampling noise, which 5 observations did we draw from our assembly line. So in this particular situation, when we only used 5 observations in the sample here, okay, the EPA's mileage estimate would be at 30 miles per gallon. Remember, they round down, and they would not be giving the automaker this tax credit. So again, one reason that that lower limit of that 95% confidence interval was less than 31 was because the sample size of 5 was not large enough to make that margin of error shrink. And if we wanted to, we could think about making that margin of error smaller by doing two things. We could increase the sample size, or we could reduce our confidence level. But given that the EPA restriction required us to use a 95% confidence level, let's keep the confidence level at 95 and think about this question of how we can figure out what sample size would give us an appropriate margin of error to pass that threshold. Okay, so if you remember, the margin of error itself was equal to the t value, okay, or the z value, depending on which framework we're in, our t value or our z value, multiplied by the standard error, okay, which was the standard deviation divided by the square root of n. So we had ts over root n, or we had z sigma over root n, or maybe we had zs over root n, depending on which situation we were in. So I'm going to go back to the scenario where we think about knowing the standard deviation sigma. So we're going to assume we know the population standard deviation here, and we're just using our z value. So if we started with the margin of error being equal to z times sigma over square root of n, what we could do is we could rearrange that equation and actually solve for n. We could move n to the other side, e to the other side, square everything. And if we do this, we wind up finding that the sample size as a function of the margin of error is equal to z times sigma over e, the entire quantity squared. Okay, so if I knew how big I wanted my margin of error, and keep in mind, the margin of error is half the length of the entire confidence interval. Okay, the margin of error is half the length of the entire confidence interval. So if I wanted to know for a particular sigma and a particular z, okay, how big does n need to be? How big of a sample do I need to give me a particular margin of error? This equation will let us figure that out. Will let us reverse engineer the sample size to match a particular margin of error. And as a general rule of thumb, we're going to round up to the next integer value to make sure we have more than enough observations to shrink that margin of error down sufficiently small. Okay, so let's go ahead and take a look at a quick example here. If the standard deviation was 45, question is, what is the sample size needed to be 90% confident with a margin of error equal to 5, meaning our confidence interval would have a length of 10 in total from the min to the max value. So a couple things we need to do here. Okay, first thing we need to do is figure out what is the z value that corresponds to a 90% confidence interval. And the 90% level was one of those common thresholds. So hopefully you can look back and reference that the appropriate z value to use here is 1.645. Okay, our margin of error is 5. Note that's not equal to the length of the confidence interval. The margin of error is half the length of the confidence interval. So now we're in a position where we can substitute these values right in here, in for z, sigma, and e. We square everything, and we wind up finding here that we need about 220 observations in order to generate a margin of error of 5. So in order for us to build a confidence interval that has a length of 10, where we're 90% confident with a standard deviation of 45, I would need 220 observations at minimum to reduce that uncertainty down to a confidence interval of length 10, or a margin of error smaller than or equal to 5. Okay, so let's go ahead and apply this to another situation here. A marketer for Vegas wants to know the average amount that tourists spend during the New Year celebration. Let's assume here that the population standard deviation, sigma, is equal to $400 in spending variability. And the question asks, what would be the sample size required so that we can build a 95% confidence interval within a $50 margin of error? Meaning our confidence interval is going to be $100 wide. Okay, mu would be smack, or x bar would be smack in the middle. And we want to know how many observations will we need to do this. Okay, so again, First thing I have to figure out is what is the z-value, the number of standard deviations away from the mean that define the upper and lower bounds of the confidence interval. And for a 95% confidence level, that corresponds to a z-value of 1.96 right over here. Okay, so we can plug those values again into our reverse engineered margin of error formula that is now solved for n, the sample size. And we see here that we need about 246 observations to make this happen. We get 245.86, but remember, we want to make sure we have enough. 245.86 gives us exactly a margin of error of 50, but we want it to be a little bit smaller than that, 50 or smaller. So we would round up to make sure that that's the case, and best answer here is we would need 246 observations. Okay, now, let's suppose for a moment that I wanted to cut that margin of error in half. Okay, meaning instead of a confidence interval that is $100 wide, right, with a margin of error of 50 on either side. Okay, suppose now I want to cut that confidence interval in half. So now the margin of error is only 25. Okay, meaning the confidence interval goes from being 100 down to 50, with just 25 on each side. Okay, question is, how much data would I need to collect? How many observations would I need to support that particular level of margin of error for my point estimate? And we're going to see an important kind of rule of thumb pop out here. And you can figure this out with some calculus, but that's a little bit beyond the scope of what we're going to get into. But a good rule of thumb here is if I want to reduce the uncertainty of a point estimate by half, I want to cut the uncertainty in half. I want to cut that confidence interval in half. Okay, this is going to require not twice as much data. Okay, you'll notice things are squared over here in this formula. There's that square there, which means when the margin of error goes down a little bit, that requires the sample size to go up disproportionately. Okay, and a general rule of thumb we're going to think about here, and we'll see this when we change the example in a moment, is if you want to cut your confidence interval, your uncertainty in half, that's going to require about 4 times as many observations. Okay, what does that mean? Well, it means the cost of data acquisition is not linear. It's not proportional, linearly proportional with respect to the size of the uncertainty that I'm willing to accept, with respect to the size of that margin of error in the confidence interval. So let's go ahead and look at this question again. Same question, okay, except instead of that margin of error being within $50, we're now going to construct the sample size required to support a margin of error of only $25. Okay, so again, same confidence level, same z-value here. And in the last problem, it required about 246 observations to support a margin of error of $50. And I suggested we would need about 4 times as many observations to support a margin of error that is half as wide. And again, if you substitute these values back into our reverse engineered margin of error formula, you should see that this comes out to about 4 times as many observations here. And again, we round up to give us this value of 984. Okay, now this is all well and good, but we're kind of back to this Z framework where we know that population standard deviation sigma. And the reality is sigma may not be known. Okay, if it's not known, well, what do? We estimate it. Okay, or maybe we guess. Okay, we can use a value for sigma that is expected to be at least as big as the true sigma. One thing we could do is we could select a pilot sample and try to estimate sigma with the sample standard deviation. We're actually going to do that in a moment. We could think about using past data or form an educated guess. Another estimate of sigma can be taken from the range. You can try to divide the range by 6 and get some reasonable estimate of sigma here. But we're going to go ahead and really apply this second idea here of selecting a pilot sample. We'll use that to calculate the sample standard deviation. And then we can think about reverse engineering the sample size given that estimate. Okay, so let's go back to this mileage problem. Okay, let's suppose that the automaker wants to find the sample size needed to make that margin of error in a 95% confidence interval equal to 0.3. Okay, doing so will raise the lower limit so that it is at least equal to 31 miles per gallon, as we will see in a moment. We don't really know this at this point, but I'm going to show you that that is actually the case. So let's now assume that sigma is unknown, and we're going to use this sample of 5 mileages as our pilot sample to estimate sigma using the sample standard deviation S. And again, since we only have 5 observations, we are not in a position to exploit the central limit theorem with respect to sample means. So we're going to go ahead and replace Z, our Z value, we're going to place that with T, okay, in computing our required sample size to support that margin of error. So a couple things are different here compared to the formula on the last slide. We're using T instead of Z. We're using S instead of sigma. And again, we know now our required margin of error was 0.3, and our sample standard deviation is 0.68 that we've estimated. This is the values that we're using from the other iteration of the problem here that we just looked at. Again, if we're going to construct a 95% confidence interval with only 5 observations, that means we're going to use 4 degrees of freedom. So again, I need to look up this T value where we have 4 degrees of freedom. And we have a tail probability of 2.5%, which means both tails add up to 5%, which means we're dealing with, again, a 95% confidence interval. So you should be able to go to that T table, maybe pause the video here, make sure you can find that, and you should get a T value of around 2.776. So once we have that information from our pilot sample, okay, what do we get from the pilot sample? Well, we got this value. We got the sample standard deviation from the pilot sample. Now we can plug and chug, and we can reverse engineer that sample size, and we get a value of 39.593 here. And again, our rule of thumb is we always round up to make sure that we are no larger than our required margin of error. And this tells us here that the required sample size is 40 observations. We need to sample 40 observations. So if we did randomly select a sample of 40, and we find the sample mean is 31.308. Okay, if we added 0.3 to that and subtracted 0.3 from it, we would be above that 31 mile per gallon EPA requirement, and we would be able to then qualify for that tax credit, for that type of subsidy. Okay, so let's go ahead and apply this idea again. Okay, let's think about determining the sample size necessary to estimate a population mean to within a margin of error of 10, given that the confidence level is 95%. Okay, let's suppose we had a pilot of size 25, so we had 25 observations, again, underneath the 30 required to use the central limit theorem. And it turns out from that sample of 25 observations, we got a sample standard deviation of 100. Okay, so this is what we're given. Okay, we're trying to look for a margin of error of 10, and from our pilot sample from those 25 observations, we had a sample standard deviation of 100. Again, we now need to use our T table at the 95% confidence level. So I'm going to go to that column for 95% confidence level. I'm going to go to the row that corresponds to 24 degrees of freedom, right? 25 minus 1. And take a minute and do that. And you can pause the video if you need to right here before I show you the result. But the T value that corresponds to 24 degrees of freedom at the 95% confidence level is 2.064. And we can now substitute these values into our formula for our reverse engineered margin of error, which solves for n in this particular case where we couldn't use the central limit theorem, right? We used the T distribution instead of the Z distribution, and we used S as our best guess at what sigma is. So if we plug that in here, we wind up getting a value of 426.01. We round that up to 427. And that means we would need a sample size of 427 in order at most to have a margin of error no larger than 10. That is it for interval estimation. Hope you enjoyed. I hope that was informative. Stay tuned for more.